Greetings, Bio 100 team. It's exciting to be here with you. I thank you in advance for your attention and for being patient as I learn this new format of bringing you information and content. In fact, I'm actually sitting at home with my awesome dog Mojo. Yes, that's his name. And he's a schnoodle, which is a schnauzer mixed with a poodle. A schnoodle. I'm not making that up either. He's just delightful. And he's at my feet now, and if he barks during the video, well, so be it. And you might be consuming this content at the beach, in a library, at home, while driving home from work, through the car speaker. All those are acceptable. And so no matter how you are processing this, thank you for being here. My name is Rob Crawford. I'm one of the faculty members here in the biology department. Since this is my first video in the series for the whole course, I just wanted to let you know how excited I am to be doing this. First of all, we get to work with a great team of students, and the faculty who are doing this are all really dedicated to, in this context, bringing you relevant tools that will help you apply science, hopefully in the real world. And at least in some small part, get ahead of this. This meaning the feeling you might have one day when you've got your degree in hand and you go out there and get that first job, or you go to graduate school and you think to yourself, wait, why didn't I learn this in my classes? I wish I had learned this application of this thing in biology from my courses. I felt that a lot when I started to go out into the workforce, and one of my first jobs was a lab technician, and the first thing they had me do was prepare solutions, and we're going to talk about that. And with that came a fear of having to do math. I remember being so scared. And I'm going to let you in on a little secret here. I don't care what level of science you might be at, whether it's entry level from a bachelor's or even a seasoned professor. Math isn't easy, math isn't fun, and I understand that there's a trepidation that might come with it, and a little bit of stress and angst. And so we're going to try to break that down for you so that you don't feel as overwhelmed by it. Practice makes perfect, and the great thing is that out there in the job force, you always can check your math, whether that's online or with your coworkers. And so we're not going to have an exam on this necessarily, and therefore you should feel free to do the same. Use this as an opportunity to build your skill set, but you don't have to do so in a silo. I'm here for you. The fellow instructors are here for you throughout this course, and so will your classmates. And so use your resources, and we'll be here for you. As you can see by looking at the title, here we are, 3.1, Lab Calculations and Overview. Stock buffers, dilutions, and working solutions. And if you say those three things really fast, stock buffers, dilutions, and working solutions, oh my, it makes you think of the Wizard of Oz, perhaps? I don't know. It did me, at least. Lions, tigers, and bears, oh my. Sorry. I'll keep those terrible jokes to a bare minimum, I do promise. A moment ago, what you see written before you represents some fundamental skills that are often asked to be employed in the workforce and in your classes. And so going forward, after you take Bio 100, you might use these both at the lab bench in a class and then in your jobs. And we hope that to be the case, and we hope to really, really help prepare you for those things. And I know I just said this, but I'll say it again. I want you to breathe. I want you to take a deep breath, okay, as we go through this math and go through the setup. I know math can be extremely stressful and scary, and so we're going to try to make this as pain-free as possible for you and give you strategies that will make you feel better about it. In fact, I'll give you one right off the bat. I like to listen to Daft Punk while performing calculations, and yes, I said that. It just puts me in a good zone to do the math. and it makes me feel less stressful. So whatever your trick is, do it. And in fact, I would be playing some Daft Punk through the speaker right now for you if I wasn't so worried about being sued. I just don't know how this all works. And until I figure that out, we're going to have to hold the Daft Punk. But you can play it all you want at home. Having said that, what are we going to learn? What do we hope to get out of this? What are some of the objectives that we fellow instructors hope you come out with following the watching of this module and some of the interactive questions that come? Well, let's just start from the top. How about a quick review of the metric unit conversions, meaning the multiplication factors? How do we go from a liter to a milliliter? What is the distance between them, mathematically speaking? What about that microliter, that nanoliter? We're going to start there, and hopefully this comes as a bit of review, but if this is the first time you've seen it, that's all right too. Our goal is to get everybody on the same page, no matter where you're coming from in your coursework. The second thing we would really like to do is to help you learn how to prepare stock buffers. Very, very commonly done in labs. In fact, when you walk into a lab, you're going to see them. Maybe there's a saline solution, and maybe there's some liquid media to grow bacteria. And often these are prepared using specific molarities or percent solutions, say, for example, a 40% weight by volume. And so we're going to do that, and we're going to help you learn how to calculate those things. And then we're going to do dilutions to create working solutions from those lab stocks. And so the goal here is, if you're making a lab stock at a higher concentration, but your experiment demands that you use it at a lower concentration, how do you actually do that math to perform that dilution? Buffers, dilutions, and solutions. Oh my, indeed. So let's keep going. Ounces, cups, pints, these are common amounts for measurements that you're going to find at home when you're following a recipe, making some sort of delicious dish for dinner. Getting hungry right now just thinking about it. And when you're in the lab and you prepare solutions, you have recipes to follow, and that's a good thing. You can consult the lab's binder and follow that recipe to your heart's content. You don't have to have it committed to memorizing something. It's going to be there for you, okay? But the measurements that you see are not going to be the ones that we just listed for cooking at home. We're going to use things based on the metric system. And so it is really good idea right now to kind of dust off the old memory a little bit, get some cobwebs out of our head, shake it all out, and remember some basic rules for working with the metric system. And when it comes to scaling, I want to keep it pretty simple for you. And so this is by no means a comprehensive chart. This is by no means a comprehensive list, but we've kind of tried to streamline this for you into a handy dandy conversion chart for things that you're going to find more common in the lab. And if you're already feeling a little bit of stress, a little bit of worry, that's okay. Pause, talk to your friends, talk to us, come on in and visit those office hours. The great thing about science and the great thing about the way we're teaching this class is it is, as I've said, a collaborative exercise. You're not in the lab on your own. In fact, even to this day, when I have to calculate anything, I run by my students, I run it by my colleagues, and I triple check my math with those around me to make sure it looks good. Sometimes I forget these rules too. So let's start out, and we're going to jam from 1 liter or 1 gram. Okay, let's just keep it right there. So let's say we were scaling on a metric level away from 1 liter, designated typically as lowercase l, or 1 gram, typically designated by lowercase g. I'm going to give you 3 columns here: a prefix, a symbol, and a metric distance away. And again, we're going away from a liter or a gram. Okay, so here are the 3 most commonly used designations, and particularly as you're working in molecular laboratories, okay, on this kind of scale. We're going to start with milli, and you've heard of milli before. If you put milli in front of liter, you have milliliter. the symbol is lowercase m, and so milliliter becomes ml for milliliter. It would be mg for milligram, and I think you've worked with these designations before in your lab classes. The metric distance away is 1 times 10 to the third, or 1,000. Another way to think about that is 1 and then add 3 zeros, or 1 and move the decimal place to the right 3 spaces away from 1. 1.0 becomes 1,000 as you move that decimal place 3 to the right. Why would I go to the right? Well, because my exponent is a positive number, so I have 3 there. 1 and then add 3 zeros, make it a bigger number, make it 1,000. If that was -3, well, I would move my decimal point 3 spaces to the left. If it was 1 times 10 to the -3, that would be 0.001. But that's not what we're doing just yet. We're going to come back to that concept, but I just wanted to make sure we were okay with exponents and powers of 10, this being 3 powers of 10, or 3 decimal places to the right, 3 zeros to the right, away from 1. Pause this, do a little bit of math on a piece of paper, crank up that Daft Punk or whatever music you like to listen to while you're doing this, and convince yourself you got that. Okay, take your time. I hope you paused it. I hope you're back. I hope you took a little time to think about that before we move forward to our next most common designation, and that's micro. I'm a microbiologist. I love microbiology. I love bacteria. The bacteria are the bee's knees. I'm sorry, I shouldn't have said that. That's really embarrassing. Old man talk here. And actually, it's even more embarrassing because this has nothing to do with microbiology. Micro is a designation we use in the metric system, and we use it very commonly. The symbol is that fancy little U there with the thing on the left, up and down, that little vertical line. We call this mu. Okay, so mu is that fancy U, little fancy symbol there. And in Microsoft Word or PowerPoint, you can insert symbol and find mu there. If you put it together, you get microliter, so mu L, or you can get microgram amounts, and that would be mu G. The distance away is 1 times 10 to the 6th. And again, that's a positive 6. So our exponent is telling us, hey, this is 6 powers of 10. Let's move that decimal place to the right 6 times. Let's add 6 zeros. We are away from 1 liter or 1 gram by 1 million times. You might want $1 million, but that would require you to know what movie reference I'm talking about, and I'm not sure you do, because I watch lame movies, although I consider this one to be pretty good. Okay, so 1 times 10 to the 6th. Nano is another common one, designated by the lowercase n, and its metric distance away from 1 liter or 1 gram becomes, and you may have guessed it, and you are correct, that's a billion. So that's 1 times 10 to the 9th, or 9 powers of 10, or 9 zeros, 9 decimal places to the right of 1. Hit pause again, and you can do that anytime you like to let this chart sink in a little bit and to maybe take out a piece of paper and scratch out a little bit of numerals for yourself. You don't have to take my word for it, okay? So the metric distance numbers I'm giving you are away from the top, 1 liter or 1 gram. It's also important to note on this scale the distance between each of these units, because in the lab, we don't just think necessarily away from 1 liter of something. We might just think about milliliters and microliters. If you have an Eppendorf tube and it contains a small volume, let's say 1 milliliter, I have no real need necessarily to think about liters. I might want to know how many microliters are in that 1 milliliter in my Eppendorf tube. I might have a bigger flask of something, and that's when I'm thinking on the liter level. So remember, it just depends on the situation and what you actually use. Okay, scale accordingly. So between a liter and a milliliter, we've already done this one for you, you have 10 powers of 3. 3 powers of 10, excuse me, or 10 to the third. And between milli and micro, it's 1 times 10 to the third apart, or 1,000. So in other words, between milli and micro. So we can scale between these units as well. And so I want you to hit pause, and I want you to look at this chart, and you probably see where I'm going with this, but I want you to write down for yourself what's the metric distance between micro and nano. And if you said that it was a factor of 1,000, or 1 times 10 to the third, you were right, okay? So you can see how this all divides up. Importantly, you can think about these numbers going down the scale or up the scale, and that becomes very important. In other words, we've went down the scale, right? We wanted to know how many milliliters were in 1 liter. We wanted to know how many nanoliters were in 1 liter. But what if you wanted to go the other way? And you wanted to know how many liters were in 1 nanoliter? What if you wanted to know how many liters were in 1 microliter? We'd have to go the other way. We'd have to, instead of going from making the chart look bigger in number, we would have to make it go smaller. In other words, there's a lot of nanoliters in 1 liter. In fact, there's 1 times 10 to the ninth of them. But if you were talking about 1 nanoliter and you wanted to know how many liters were in that, well, that's going to be a really, really small number. In fact, it's going to be 1 times 10 to the ninth, but -9, okay? So let's go through a couple of examples and crystallize this a little bit for you, okay? So I'm going to ask you, what if I had 1 liter and I wanted to know how many nanoliters are in there? Okay, we've done this one and it's on the chart, but I want you to write it out for yourself. So go ahead and pause it, crank up that Daft Punk again, okay, and write it down. How many nanoliters are in 1 liter? 1 liter equals, pause it. That's right. 1 liter equals 1 times 10 to the ninth nanoliters. And if I flip the script on you and I said, wait, that's great and all, but I want to know how many liters are in 1 single nanoliter. 1 nanoliter equals how many liters? First ask yourself, is that going to be a big number or a small number? It's going to be a really small number, right? If I only have a single nanoliter, and I already know that there's a lot of nanoliters in a liter, and if I have only 1 nanoliter, I don't have very many liters. So let's go, pause it, write it down, do that little math for yourself to come up with this. 1 nanoliter equals 1 times 10 to the -9th liters. If you move your decimal place from 1 to the left 9 spaces, you end up with 0. And then that is 8 zeros and 1 liter. 0.000000001. My dog just looked at me like, what are you doing? Why are you counting out so many zeros? Look how small that number is. This scaling up or down is so important in a lab. Lastly, the example becomes about that Eppendorf tube, okay? So the Eppendorf tube, go into that lab, you pick it up, small little piece of plastic, and you open up that cap, and you see 1 milliliter of a substance. Maybe it's distilled water. You have 1 milliliter. How many microliters are in that 1 milliliter? Okay, look at the chart. Ask yourself, are you going up or down? Ask yourself, how many powers of 10 am I moving? What's the metric distance? Is this going to come a smaller number or a bigger number than 1? Okay, so what we want to know is how many microliters do you find in 1 milliliter? Okay, go ahead and pause it and do that work. Welcome back. I hope you actually did that. And here is, as you see, the giveaway. 1 mil is equal to 1 times 10 to the third microliters. And you saw that little blue bar come up on the left. And that's just to remind yourself how much the scaling is between these units, okay? The distance between a mil and a microliter is 10 to the third. You just have to ask yourself, from which perspective am I looking? Am I asking how many mils are in a microliter, or vice versa? What's that? Well, this is my little designation for tips. That's a little yellow tip you'd put on the end of a pipetter, and this is my opportunity to give you a little pro tip. See what I did there? A pro tip is a useful bit of information, and a tip is a tip, and there's a picture of the, well, okay, so you're telling me to move on, and so I will. Online conversion calculators, okay? In the lab, when you're not in a class, and maybe when you're in a class with a good instructor, you can pull out the old phone or the computer, consult Dr. Googs, meaning Google, or Dr. Googs as I like to call it, and type in convert milliliter to liter. And there will be some very handy dandy conversion calculators where you can enter the numbers you're working with and it'll spit out a result. I just don't want you to rely solely on them. It is really important to know how these scalings take place in a lab setting, okay? That nano and liter distances, the milli and micro distances, these become very, very important when you're pipetting. And we're going to get into some more examples very shortly. Have you fallen in love all over again with the metric system? I know I have. In fact, honestly, I never fell out of love with it. I really wish we did everything in the metric system, including shoes. I mean, I get that a foot and a foot is the same, but, you know, that's kind of arbitrary, and, well, this isn't the place for that. So let's move forward, you metric system lovers, or at least tolerators and users of. How about that? Here we go. We're going to make Molar Solutions. We're going to get this buffer making party started right. We're going to just go back to the basics, a 1 molar solution, and that might sound scary. It was for me when I first started in my lab. The first job I had, the first thing I was asked to do was make a 1 molar solution of sodium chloride, and I freaked out. And it went a little something like this. Hey son, we need you to make a 1 molar solution. That's my best impression of my boss. This was in Ohio. That's what it sounded like. And my response sounded like this. Yes, sir. Yeah, something like that. My voice was cracking and very angsty at the time. So that's my best rendition. And I freaked out. Did I mention that I had freaked out? So I returned to my knowledge of some basic chemistry principles, and again, those in the lab around me, and I worked through it. So let's do that for you right here. Okay, we're going to think about this in the context of a 1 molar solution, 1 capital M. And we're going to revisit some rules and what this all means, including molarity being moles per liter. And then we're going to scale from there. So we'll start with what makes a 1 molar solution, and then we'll think about what happens if you wanted a 0.1 molar solution, or a 1 millimolar solution, or you didn't want a liter of something, you wanted 500 mils of something, because you didn't need that much, or you didn't even have a vessel that big to contain all that liquid. We can scale from 1 molar. So that's how we're going to do it. When you start to think about the elements you need to make a molar solution, and yes, that was a heavy-handed pun. Low-hanging fruit, I just had to do it. I'm sorry. But when you're gathering those elements that you need, the components, I guess, would be a better way to say it, of a molar solution, you're going to look at none other than the periodic table of elements for some information and for some guidance. And when I think of the periodic table, I think of the chemistry classes I had in my career, and that there was always on the wall on one side of the room a periodic table of elements, and it scared me, and I thought I was going to have to memorize the whole thing, and I hope you didn't have to do that. I had to do parts of it, and that was really hard for me. But we're not going to do that here. I'm showing you sodium, and the reason I'm doing that is for an important reason. when we're thinking about molarity, we need to look at the periodic table to get a number that's going to help us. And so what number is that? Well, you see two numbers here. You see 11 and you see 22.990, okay? It turns out that 11 is the atomic number of sodium, and that 22.990 is the atomic mass. And the atomic mass is associated with units. And those units are grams per mole. Please, anytime you're doing math in the lab, units come first. You read a question on a quiz. You are asked to calculate molarity. Whatever it might be, think about the units first. What is the answer going to look like in terms of the units? Then you find the number that goes with it. Okay? Atomic mass is grams per mole. We're trying to get moles per liter. We already have some things that are working for us in our favor. So we need the atomic mass. And now that we have it, we have to use it. And to my knowledge, and in my experiences, weighing elements is much less common than weighing compounds containing combinations of elements. And one very, very common compound of elements is sodium chloride, as I just mentioned before. So you're going to find sodium in there, and you're going to find chloride in there, and sometimes it's going to arrive as a powder, as is the case here. And this gray container is a very commonly found item in labs, on shelves or in cabinets, things like that. And so I remember having to use a bottle that looked just like that, and that was the starting place. And I needed something off of that bottle. And I look at this bottle here, and I see some writing there, and it's kind of hard to read, but I see 500 grams, and that's the amount in a full bottle. I see the lot number from the company. That's helpful in case I need to know when it was made. And oh, I even see that this came from Dubuque, Iowa. Nice. Kind of close to Ohio, but far from here. Those are both states. Iowa and Ohio are states. Okay, now that we've got that out of the way, what I want is the molecular weight of sodium chloride. To make a molar solution, I need molecular weight. And what is that? Well, it's the additive amount of the atomic mass of sodium plus chloride, the two elements that we're talking about. So let's write that out. It looks like this. Sodium chloride, or NaCl, is the atomic mass of sodium at 22.99 grams per mole, plus the atomic mass of chloride at 35.45 grams per mole. So go ahead and pause this video, and to your favorite music, you know what mine is at this point, go ahead and add those two things together, and let's get the molecular weight in grams per mole. Write down grams per mole first, and then go ahead and add this together. You can do it by hand. You could punch it into a calculator on your phone or whatever device you're using, and you should come up with 58.44 grams per mole. Does that look good? Are we all on the same page? 58.44 grams per mole is the molecular weight of sodium chloride, and an important component when we're thinking about making a 1 molar solution of sodium chloride. All right, excellent. Let's do the work of making a 1 molar sodium chloride buffer together. We're just going to do it together. And in fact, I'm going to be so generous as to show you, because I know I was a visual learner back in the day, and you might be too. I will show you what I looked like the first time, approximately. This picture is approximately at the same time I was first asked to do this at a job. And I look like that. And I'll just let you laugh all you want. Go ahead, it's fine. You gotta learn to laugh at yourself. And if you're noticing all those pimples and that greasy hair, well, you know, that's what comes with working at McDonald's and eating fast food and just trying to pay your way through school, and your mom putting a bowl on your head and cutting around the bowl and calling that a hairstyle. She didn't really do that, but it kind of looks like I put a bowl on my head and cut around it. Anywho, I understand. This is not a simple matter here, and so make a 1 molar sodium chloride buffer. Who, me? Yes, let's do it together. So we already mentioned the importance of the molecular weight. Here we've put it down as 58.44 grams per 1 mole. And you can see why these units are really, really important. And you may remember back in your general chemistry class doing this long form, where if you have a 1 molar solution, you're looking for 1 mole per 1 liter. Moles will cancel out, leaving you with 58.44 grams of what you're looking for, in this case sodium chloride, 58.44 grams of sodium chloride, and then you'd add a solvent, potentially distilled water, or maybe it's a phosphate buffered solution of some sort, and you're going to bring that up to volume in a total of 1 liter. So that's how you'd make a 1 molar solution at 1 liter. And because we like pictures, and because I mentioned my dog, I teased my dog, and I said he was the best dog, and his name was Mojo, and you were definitely wondering what he looked like. Well, here he is. And you know, it's important that when doggies do something good, you give him a treat. And in this case, I'm gonna just show you my dog Mojo as an excuse to show you the best and most cutest dog in the world. And he's telling me, oh, you're a good boy, and you get a treat. Good boy, make a solution. Okay, enough of that. Now that we've made our 1 molar solution, it's important to think about how we can demystify and make the math less scary by scaling from there. And we could do this in one of 2 ways. You could scale and move decimal places around and think about fractions of a total from 1 molar. Or you can always do it long form, just like you were taught in chemistry, where you would just, let's say you wanted that 1 molar solution up there in a different volume, you change out those units and scale accordingly up there. So we're going to do 2 examples together for scaling, okay? The first one is the instance where you don't want 1 molar sodium chloride, but your task is to go over to that shelf, grab that powdered sodium chloride off of the shelf, get your solvent, and create a 0.1 molar sodium chloride solution, okay? Not a 1 molar, but a 0.1 molar. And so if I saw that, I know I still need my molecular weight, and we have that. But if I know that 58.44 grams up to 1 liter is 1 molar, well, I can start to think, how far away from 1 molar is 0.1? And so in my mind, I think of this by, oh, hey, look at that. It looks like powers of 10. And it is. When you think about powers of 10 and moving decimal places, the math becomes less mathy, in fact, and more of a power of thinking about what it means. And that's the most important part. We can grab our calculators and they could do the work for us, but we really, really need to understand what we're putting into those calculators, because if you don't know what buttons to press, you're not going to get that right answer. So however you think about it, just remember there's always more than one way to eat a Reese's. And I know that's another old reference to a Reese's peanut butter cup commercial, but I am old, as I told you. So if you look at the number 0.1 shown in orange, and you compare that to 1 molar, well, that's a tenth. 0.1 is the same as 1 over 10, and 1 over 10 and 0.1 is the same as 1 times 10 to the negative 1. And 1 times 10 to the negative 1 from our discussion before should get you thinking about moving a decimal place to the right or to the left. That's right. Move it to the left, not right. So move it to the left. 1 times 10 to the negative 1, we are going for a smaller number. We would move it to the left of 1 and get 0.1. And you can see that all the way across. And so what this is really saying is a 0.1 molar NaCl solution, unless they've told you a different volume, and we haven't, is a tenth of the power, a tenth of the strength. And therefore, we're thinking about a tenth of the sodium chloride. So if we're keeping our volume the same, and you can look back up there at the top, we've got 58.44 grams up to 1 liter of volume for 1 molar, and we want a tenth. The only thing we're changing is the numerator up there. And we're thinking about moving the decimal place over to the left by 1 place. You come up with 5.844 grams up to the same volume. In other words, you're taking a tenth of that powder, you're going up to the same volume, and therefore it's a tenth as concentrated, or I should say a tenth of the molarity, and so you have a 0.1 molar sodium chloride solution. If you want to do the long form, please do so now. Go right ahead. The second scaling is volume. So the first one was about the sodium chloride and how much of that we wanted to scale from. This one is about the volume. And of course you could scale both, but we'll just show you these two and then you could do some practices, and we have those for you both on the online worksheets and in class. And so here we're going to keep it as a 1 molar sodium chloride solution, but we're going to cut the volume to 500 mils. We don't want a full liter. We don't even have a flask capable of holding a full liter. We just want to go up to volume of 500 mils. Mils, liters, mils, liters, mils, liters. Conversion between mils and liters, this sounds just like that handy dandy conversion chart through the metric system that we went over just a bit ago. And yes, it is, and let's put it to work for us. Let's do it, because the only thing that's changing here is that we want a different volume. We still want a 1 molar solution. Okay, so here's how I would think about it. 500 mils is the same as 1 times 10 to the negative third liters that pause was because I hope you caught that 1 times 10 to the negative 3 would have been the distance away if we were talking about 100 mLs. But here, that would be 5 times 10 to the negative 3 liters, as shown there. And that's equal to 0.5 liters. Move that decimal place over 3 from 500, 1 space, 2 space, 3 spaces, you get 0.5 liters. Fantastic. So we're thinking about half the volume, half the solvent. 500 mils is half of a liter. And so what we can do here then is return to our top 1 molar solution. We're still 1 molar. And if we've halved the amount of volume, we have to half the amount of powder that we grab to keep everything the same, to keep apples to apples. If we half the volume, we need to half the amount of sodium chloride that we actually put in there. And so 58.44 divided by 2 is 29.22. So you'd want to take 29.22 grams, put it in your vessel of choice, and then add your solvent up to 500 mils. That would keep it 1 molar, where each of the amount of sodium chloride and the volume of solvent are halved from what you see up at the top.